Okay, I should have labs. Today, what we're going to do is today's information starts exam number 3. Today, the first thing we're going to do is we're going to discuss the acid-base definitions. We're going to talk about the Arrhenius acid-base definition and the Bronsted-Lowry acid-base definition. Later in this chapter, it brings in the Lewis acid-base definition, but we'll talk about that later in this chapter. So again, we're going to start with the Arrhenius definition. That's supposed to be Arrhenius, not Arrhenium definition. And then we'll go to the Bronsted-Lowry definition, and the Bronsted-Lowry definition leads into the concept of conjugate acid-base pair. Once we talk about a conjugate acid-base pair, we're going to take time to learn to identify the conjugate acid-base pair in a chemical reaction. After we've identified conjugate acid-base pairs, then we're going to start talking about acid strength. And we'll talk about how to determine acid, or how to determine which in a pair is the stronger acid given a couple of pairs. Finally, we'll hopefully get into the conjugate acid-base pair and determine which direction the reaction is most likely to proceed given the strength of the acid and base. So that is the goal for today. So it's all about definition, conjugate acid base pair, and then finally getting into acid strength. Any questions before I start? Okay. So the Arrhenius definition, yes. Oh, thank you. No, it's not. Okay. The Arrhenius definition of an acid is that it donates a proton. The Arrhenius definition of a base is that it donates a hydroxide group. For the most part, in College Chemistry 1, when you talked about acid-base neutralization reactions, you were using the Arrhenius definition of an acid and a base. The acid donated the proton, the base donated the hydroxide, the proton and hydroxide combined to form water. And that's why it was a neutralization reaction. The Arrhenius definition is very limiting when it comes to the base. A much easier definition when it comes to the base is that of the Bronsted-Lowry definition. First of all, the Bronsted-Lowry definition of an acid is that it still donates a proton. But the base, the definition of a base is that it accepts a proton. That leads us to the definition of a conjugate acid-base pair. A conjugate acid-base pair is a pair of substances that differ by a single proton. Example, sulfuric acid and hydrogen sulfate are a conjugate acid-base pair. Yesterday in lab, you worked with a conjugate acid-base pair when you dealt with hydrogen sulfate and sulfate. Those are a conjugate acid-base pair because they differ by a single hydrogen. Another conjugate acid-base pair would be hydrochloric acid and chloride. Another one is water and hydronium. These are all examples of conjugate acid-base pairs. They are substances that differ by one hydrogen. Now let's deal with a reaction at Bronsted-Lowry acid-base reaction. Let's take acetic acid and ammonia. In this problem, the acetic acid is an acid. The ammonia is a base. Let's use the Bronsted-Lowry definition that an acid is a substance that donates a proton, and a base is a substance that accepts a proton. If so, then the acetic acid is going to donate its proton, and it is going to become acetate. In this reaction, the ammonia is a base, so it accepts a proton and becomes ammonium. Notice the proton carried with it its charge. Now for our conjugate acid-base pair. If acetic acid is the acid, then the conjugate base must be a substance that differs by a single hydrogen. So the acetate would be the conjugate base. If ammonia is acting as a base, then the conjugate acid is going to be a substance that differs by a single hydrogen. So the ammonium is the conjugate acid. If I give you the reaction, HCl plus water goes to make hydronium and chloride, I expect you to be able to identify the acid, the base, the conjugate acid, and the conjugate base from their definitions. First thing I do is I find the pairs. HCl and Cl minus is the pair. I notice that HCl lost its hydrogen. So that must mean it is an acid by the definition. It donates its hydrogen. And the Cl minus must be the conjugate base because it's a conjugate acid-base pair. Water and hydronium is a conjugate acid-base pair because they differ by a single hydrogen. Looking at water, it gained a hydrogen as it went from reactant to product. According to the Lewis base definition, a substance that gains a hydrogen is a base. Therefore, hydronium is the conjugate acid. Folks, identifying conjugate acid base pairs does not get any more troublesome than that. You identify the two substances that differ by a hydrogen and look at what happens when it goes from reactant to product. One thing you will note is that the acid and the base is always listed on the reactant side. And the conjugate acid and the conjugate base is always listed on the product side. But it does not get any more difficult than that. Now, in college chemistry 1, you talked about strong acids and weak acids. Strong acids are acids that dissociate entirely in water. Depending upon whom you've had, you were told that there were 6 strong acids. Those strong acids are HCl, HBr, HI, HNO3, HClO4, and H2SO4. You had to know who your strong acids were to be able to take a balanced chemical equation and convert it into a complete ionic equation and into the net ionic equation. Again, these 6 dissociate entirely. So when we actually add them to water, because they dissociate entirely, we use a single-headed arrow to illustrate the fact that they do dissociate entirely. And for H2SO4, the first dissociation occurs entirely. We'll talk about diprotic acids a little bit later on. If it is not a strong acid, it is a weak acid. Weak acids partially dissociate in water. To set up an equilibrium. Acetic acid was an example of a weak acid. When it is added to water, it only partially dissociates, and so it sets up an equilibrium between the acid and water and hydronium and the acetate ion. Another one that you talked about in college chemistry 1 was oxalic acid. Oxalic acid, since it is not a strong acid, that must mean it's a weak acid. Therefore, when it dissociates, it will set up a equilibrium between the acid and water and hydronium and the conjugate base. Okay. We know that HCl, HBr, and HI are all strong acids. But which one's stronger? For a binary acid, acid strength is determined by the size of the non-hydrogen element. The larger the size of the non-hydrogen element, the stronger the acid. So this goes back to atomic size that was learned in college chemistry 1 when you were talking about atomic trends. Fluorine, being a group 2 element, is fairly small. And that's an HF in those circles. As you go down the group, the atomic size increases. Any questions so far? Now the question, the why? The question is why? Well, the answer has to do with what happens when it loses that hydrogen. What happens when that hydrogen is removed? Well, you now have a fluorine ion, F minus. Compared to a chlorine ion, Cl minus, compared to a bromine ion, Br minus, compared to an iodine ion, I minus. Now, folks, the reason HF is weaker is because when it loses that hydrogen and becomes fluoride, that fluorine has to take on that extra electron charge. Because fluorine is such a small atom to begin with, it knows that it took on that electron charge. It feels that electron charge. But when you get down to iodine, iodine is such a huge atom, relatively speaking, that when it takes on that extra electron charge way out here, it really has no idea that it took on that electron charge. So because it really doesn't know it has that electron charge, it's easier for that hydrogen to pop up. So when you're looking at a binary acid, as you go down a group, because the non-metal atom size increases, so does the acid shrink. Now let's talk about oxyacids. My tablet has frozen. There we go. Can anybody tell me what an oxyacid is? Well, yes, but that's not the whole story. Okay, I will stop the suspense here. An oxyacid is an acid of a polyatomic ion that consists of oxygen and one other element. So, for example, some things I've already given you. HNO3 is an oxyacid because it's an acid of a polyatomic ion that consists of oxygen and one other element. H2SO4 is an oxyacid. It's an acid of a polyatomic ion that consists of oxygen and one other element. Now, the strength of the oxyacid is determined by the ease for which the negative charge can be spread out over multiple oxygens. This is I'm going to show you an easier way in a moment to figure it out. But basically what I'm trying to get at here is if I take HNO3, for example, and I remove this hydrogen, then what's left is this structure. But because nitrate has that double bonded oxygen there, that double bonded oxygen can, remember, basically you got to remember nitrate is has resonance structures. Because nitrate has resonance structures, that double bonded oxygen doesn't necessarily have to be in the location I drew it. Instead, it could be here, and that negative charge be distributed onto the top atom. Or we can make it there. Whoops, drew it wrong. Or we can make it here. That's not what I want to do. Sorry. Or it could be here. That's what I wanted to do. In which case, the negative could be on a different atom. But there's all sorts of options. And I drew it wrong as part of the problem here. The negative could be there, or it could be in, and anyhow, basically what I'm trying to illustrate, and I'm not doing a great job of it, there's 3 oxygens that negative charge can be distributed over. Because there are 3 oxygens that negative charge can be distributed over, it's a strong acid. Now, you're not going to want to draw out all these resonance structures just to figure out if it's a strong acid or not. Not certain you're going to like the other thing I'm about to say either. But it's definitely the easiest way to determine the strength of an oxyacid. And that is to determine the oxidation state of the central atom. The higher the oxidation state, the stronger the acid. The good news, folks, you only have to remember 3 of the oxidation state rules. Rule number 1 that you got to remember is that hydrogen is a +1. Rule number 2 that you got to remember is that oxygen is a -2. And then rule number 3 that you got to remember is that you're going to have to calculate the third element. So let's just see. Let's take HNO3 and HClO4. We know that both of them are strong acids, but who's the strongest? Okay, hydrogen's a +1, oxygen's a -2. You have to calculate the other element. We have 1 hydrogen times a +1. We have 1 nitrogen times X. And we have 3 oxygens times a -2, and that is set equal to 0. 1 plus X minus 6 equals 0. X minus 5 equals 0, so X equals 5. So the oxidation state on our nitrogen is a +5. Let's do the same thing for perchloric acid. Hydrogen is a +1, oxygen is a -2, and you have to calculate the chlorine. There is 1 hydrogen times a +1. There is 1 chlorine times X, and there are 4 oxygens times a -2, and that is set equal to 0. 1 plus X minus 8 equals 0. X minus 7 equals 0. X equals 7. So the oxidation state on the chlorine is a +7. Because the oxidation state on chlorine is a +7, that makes perchloric acid the stronger acid. Let's look at another set of examples.
let's do two that you're not going to know. I mean, we know they're weak, but who is the weakest between oxalic acid and let's do phosphoric acid. The reason I know they're both weak is because they were not one of our 6 strongs. But which one is stronger? Well, we're going to do the same thing. We got a +1 for hydrogen, a -2 for oxygen, and we got to figure out carbon for oxalic acid. 2 times a +1 plus 2 times x plus 4 times a -2, and that is all equal to 0. +2 plus 2x minus 8 equals 0. 2x minus 6 equals 0. 2x is equal to 6, and therefore x is equal to 3. So our oxalic acid, the carbon has a +3 oxidation state. Now let's look at phosphoric acid. The hydrogen's a +1, the oxygen's a -2, and we're calculating phosphorus. We have 3 times a +1 plus 1 times x plus 4 times a -2, and that is equal to 0. 3 plus x minus 8 equals 0. X minus 5 equals 0. X is equal to 5. So our phosphorus has a +5 oxidation state. Because the oxidation state of phosphorus is larger, that means phosphoric acid is a stronger acid than oxalic acid. Questions? Now, why does acid-base strength matter? Acid-base strength matters really for 2 reasons. One, because we need to know whether the reaction goes to completion. If it has a strong acid or a strong base, it's going to go to completion. But number 2, a reaction will always travel from stronger acid, stronger base, to weaker acid, weaker base. Now, I gave you ways if you're given a couple of different acids to determine who's stronger. But this diagram I'm passing out, it gives some of the most common acid-base groups. Okay, first thing I want you to note about this table is the stronger the acid, the weaker its conjugate base. So for example, we've talked about hydrochloric acid and chloride. This is a strong acid, and this is a very weak base. To the point that its base capacity is almost negligible. So on the, of course, this is shades of gray. On the left-hand side, as you go down the table, the acid becomes weaker. But if you look at the right-hand side, you will notice that it becomes, the conjugate base becomes stronger. So let's just look at an example. Let's say I have HC2H3O2, and I react that with the bicarbonate ion. This sets up an equilibrium to form carbonic acid and acetate. Is the forward direction or reverse direction? Preferred. Okay, what you do is, first of all, you identify your acid and your base and your conjugate acid and your conjugate base. Then you look at your diagram, which I will give you the diagram for this type of question. And you go, okay, between my two forms of acid, acetic acid is the stronger acid. Between my two forms of base, bicarbonate is the stronger base. So this one is going to prefer the forward direction because it always travels from stronger to weaker. Bring this on the Monday after test because I will start with another problem of this nature before I move on to the next material. And I will see you for your test on Friday.